Started. Okay, it is 1 p.m. We are live. The audio and the video should be coming through. So welcome to Statics. Couple quick announcements. Attendance grades are up to date. Homework, so same thing with before. Homework 2.6 is due today. I'm going to assign homework 2.7 after class, and then the last homework was graded and the solution is posted. One other housekeeping item. So today we're going to discuss our last topic about statics of particles, which is static equilibrium in 3 dimensions for all forces meeting at a common point. And then that's our last lecture topic for the first exam. On Friday, we're going to discuss cross products of vectors, which won't affect things until exam 2, but it's a really important topic because we're going to be using cross products a lot in the next few weeks. So it's something that we need to cover. But homeworks all the homeworks up to 2.7 will be the homeworks on the exam. With that, we'll go ahead and get this fired off. We're going to talk about static equilibrium in 3 dimensions. What we did last time was look at how to deal with forces in 3 dimensions. And by that, what I mean is how to describe forces in 3 dimensions and how to add them up. And so, we noticed that there were a lot of similarities between what we do in 2 dimensions and what we do in 3 dimensions. It doesn't really make the problems harder. It just makes them maybe a bit longer. Might be the best way of describing it. So, our vector description, we have another term. Instead of ij, it's now ijk. The magnitude of a vector, instead of just x component squared plus the y component squared and then the root of all that, we now have a z component. Again, just another component when we add forces up. We do have 3 equations of static equilibrium, and so that's going to affect a little bit about how we solve problems out in 3 dimensions. We're going to use our Casio, but we're going to have to use the 3x3 solver. And we also talked about orientation of vectors, but that was actually pretty easy because we can just use our unit vectors and then take the inverse cosine of all of those unit vector components, and boom, we get the directional cosine, or the cosine, the angles from the x, y, and z axes to the vector in question. Now, last time was about just describing vectors in 3D and adding them up. Today, what we're going to do is apply static equilibrium. And so what I mean by static equilibrium is we've got 3 equations that we have to satisfy for a system to be in static equilibrium, and that's the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, and the sum of the forces in the z direction equals 0. So now, instead of having a 2x2 system, we have a 3x3 system. So remember, in the Casio, you use the mode button, you press number 5 to go into equation solver mode, and up until now we've been using option 1, which will do the 2x2 system solution. Now we need to break out the 3x3, which is the 3 equations, 3 unknowns system. I actually have a TI-36X Pro with me right now, and I might do it with you. If you have a TI-36X, it's second, and then system solver, which is above the tangent, and then you would just do the option 2, the 3x3 system. I find that with this stuff, the best way of exploring it is to do it. Okay. Now, whenever you're dealing with a 3-dimensional equilibrium problem, you should have 3 unknowns. And so that's pretty clear just from looking at the problem. We have a balloon that's floating upwards, and so it's being tethered to the ground by 3 cables. The balloon is exerting an 800 Newton force upwards. And so what we're going to do is determine the tension in each of those 3 cables. So there's the 3 unknowns, and we have 3 equations of equilibrium. And so that'll be the giveaway that what you're doing is the right way to go. There are a couple of other ways to rewrite this stuff. Maybe you know the tension in one of the cables and you want to find the tension in the other 2 and what force the balloon is exerting. But again, no matter what, there needs to be 3 unknowns for these problems to be solved. It's kind of a dead giveaway. Let's just go right into it. Let's just jump right into the problem. Let me stop share. You might notice on the board I have some of the stuff already written down, but we're gonna explore how to get that stuff here in a second. So share screen, share the entire screen. There we go. Okay, so here's the problem. Let me take my keyboard off this this surface I'm using, make it a little easier on myself. Okay, so here's the problem, and we're going to be you know, handling this a lot like what we did before, but you know, where before we would, you know, we'd add the vectors up, we're going to bring the equations of equilibrium to assess that. First thing I want to do is I want to start writing my distance vectors. So remember, you know, in order to describe a vector in 3 dimensions, what we can do is we can write the distance vector along which that force acts. And once we have the distance vector, we can then convert that into a unit vector. And then once we have the unit vector, multiply it by the magnitude of the force, and then we get the force vector. And then once we get the force vector, it's just, you know, breaking out the equations of equilibrium. So let's start off, and I'm going to I'm going to help you out with the first one. I'm going to do AB, and then I'm going to have you all help me out with AC and AD. So let's start off with AB. So first off, maybe I should make sure that we're clear on why we're doing the vectors in this order. Well, if you look at the problem, all of the forces are going through point A. You know, here's point A. And so we've got one force acting upwards, which is the force from the balloon. And then we've got 3 forces acting outwards. We've got T, what is that, AD, and then T, whoop, come on, T, AB, and then T, AC. So the reason why I'm writing the vectors from A to B is because A is that's our point, that's our particle. So we're writing the vectors AB, AC, AD, because they're starting at A and going outward. That's the way that the forces are going. So just to make sure that's clear. So I'll work on the first one, and then I'm going to help have you all help me out with the second one. So we have the distance vector AB, which is going to be some component times I plus some component times J plus some component times K. And that's going to be the case for all of them. So maybe I'll be a little lazy and fill all that in right now. Okay. So here's my template for all my distance vectors. Distance vectors. Maybe I should put an S there. The English professors wouldn't like me if I didn't have an S there. So let's do AB. Okay, so I'm starting at A and going to B. And I just, you know, use my axes. This is the x-axis. This is the y-axis. This is the z-axis. And I ask myself, what, you know, how far do I go along each axis? So starting at point A, moving to point B, how far along do I go in the x-axis? Well, I'm using the x-axis, and that's that 4.2. There you go. 4.2 meters. But it's negative because I go negative in that direction. So negative 4.2 meters. For the y direction, I'm going down. You know, you can see I'm going from here to here down on the y, and that's negative 5.6 meters. And then for the k direction, well, I'm not going anywhere along the z-axis. Point A and point B remain along that same direction with z, so this is 0. So you can put 0 meters if you want, or just 0, that's fine. And then there you go. So there's the AB vector. So I've done AB. I'm going to ask for some help on AC and AD. So let's start off with AC. I want to see if somebody in chat can just tell me what is the AC vector. Okay, so I've got 2.4. Okay, 2.4 what? So when I say AC, like, okay, so are you talking about this part right here? I want the whole thing. Tell me the whole thing. Not just the x component. Tell me the whole kit and caboodle. Okay. All right, I've got, okay, so 4.2i, negative 5.6j, 4.2k. Okay, Mr. Ball, I think you might have a couple values off. I'm getting something different. Now, Mr. Davis, okay. Mr. Davis is closer. Mr. Dara, I think you've got it dead on. I think Mr. Dara's got it dead on, and same with Mr. Page. So, yeah. So AC, okay, so we're talking about this line right here. So along the x-axis, so that's this way, you can see that's positive 2.4. For the J, that's the Y, so that's negative 5.6. And then for the K is the Z, and the Z, we're going from A to C, we're going positive along the C, and that's positive 4.2. Oh, do better than that. Okay, now, all right, let me go to chat because I had a lot of responses on chat. Yeah, okay, you got that. Good, no worries. And so let's see, I had a lot of people respond to that. Let's see, Mr. Ball, are you good on that? I think you had just a couple values backwards, which is okay. No worries, no worries. That's fine. That's fine. This is probably, I think, the hardest part. The rest is as you're going to find here in a second, it's a lot of grunt work. How about AD? Let's do AD. Can somebody help me out with AD? And maybe some folks that haven't said anything. I mean, I want to make sure that everybody's firing on all cylinders today. So the folks that have typed something in chat, let's get somebody else in going. All right, so we got 0i, negative 5.6j, and negative 3.3k. There we go. It's exactly right. So yeah, 0 in the I. We got negative 5.6 in the J, and negative 3.3 in the K. Exactly right. Good deal. Great job, everybody. Okay. So now that we've got the distance vectors, the next thing that we're going to do is we're going to do the unit vectors. Okay. Tell you what I'm going to do. I'm going to cheat a little bit. I'm going to move this down a little bit, because I know what's going to happen. I'm going to start drawing these things out, and then, oh, I forgot to turn my draw back on. I'm going to start drawing these things out. I'm going to be scrolling up and down like nobody's business, and I'd like to not do that. Okay, so now the next step is we're going to write out our unit vectors. And remember our general formula for a unit vector, so we use lambda. That's an ugly one. I can do better than that. Our general formula for a unit vector is we take some vector and divide it by its own magnitude so that we get a vector with a length of 1. So we need to determine the magnitude of each of these vectors. Now, let's also do this. Let's just sort of write that formula out. So the magnitude of a vector is going to be just the x component squared plus the y component squared plus the z component squared, and we're going to take the square root of all that. So I'm curious, can somebody just tell me what is the magnitude of vector AB? Like, do we need to write that out, or can we just, at this point, can we just compute that? It's just going to be the 4.2 squared plus the 5.6 squared plus the 0 squared, and take the square root of all of that. And one of the nice things about this is you don't have to get super precise on the unit or on the signs because you're squaring everything. Okay, so we got some 7s. All right. Now, is the magnitude 7 or is it 7 meters? Don't forget the units. There we go. That's right. Okay, so man, I got a little nuts on the scrolling there. So if I know the magnitude of AB and I already have AB figured out, I propose then that lambda AB what do? I just take each of those components and I divide by 7. So if I take negative 4.2 and I divide by 7, I'm going to get, well, somebody help me out. So we have lambda AB. It's going to be something times I plus something times J plus something times K. Somebody help me out. Just tell me what it is. And so let's just keep in mind, like, how do I do that one? It would just be negative 4.2 over 7. This one's going to be negative 5.6 over 7. That's just going to be 0 over 7. So yeah, it's just a negative 0.6 and 0.8 and 0. Yeah, exactly right. Just going ahead and chugging all that out. And let me be clear, I'm perfectly fine if you leave it in fractional format or if you convert it to decimal. I'm fine either way. Just as long as if you do convert it to decimal, make sure you have enough decimal places so that everything rounds out. Like if you're doing 4 to 5 decimal places, you're probably pretty good. Okay, so let's do the rest of them. So AC and AD. So did I miss a negative? Oh, I did. Thank you. Yep, you're exactly right. Yeah, that's 0.8. Yep, thank you. And one of the things that you'll notice when I'm writing this out, I'm being pretty specific on the units. For instance, vector AB has 4.2 meters. Lambda AB has no units. Remember, unit vectors are unitless. They have no units. It's sort of a weird name, like unit vector is unitless, but they say unit because it has a unit length. Okay, so AC. Somebody tell me what the magnitude of AC is. Okay, 7.4 meters. And then somebody went ahead and told me AD. I think you got, what was that, 6.5? I'll go ahead and write that down. 6.5 meters. So I'll go ahead and do AC because it's got some decimals to it. It doesn't come out as pretty as lambda AC. So first off, we've got a positive, negative, positive. Those are the value, or wait. Yeah. And so that is, what is that? That is 0.3243 I plus, and then what is it? That's negative 0.7568 J plus, and then it's 0.5676 K. Did I get my signs right on it? I think I might have a typo here on the board. Okay, good. All right, and then this one I get lambda AD, and I'll go ahead and do that one as well. Okay, this one's 0, and then this comes out, what is that, negative 0.8615, and then this is negative, what is that, 0.5077. Yes, wonderful, thank you. Nope, I scrolled too far. Okay. And so if you have the unit vectors, you can go ahead and do the force vectors. And I know this is probably going to seem a bit repetitive, but there's a reason why I'm doing this, trust me, on this one. So now we're going to do the force vectors. Okay, so remember, a force vector is just the magnitude times the unit vector, okay? And there's a reason why I'm doing this. I know I'm going to be doing a lot of repeat writing, but you'll see. So remember in this problem, how many forces do we have? We actually have 4 forces. We have the tension in each of our ropes, but we also have the balloon force, the balloon acting upward. So we've got the tension in AB, the tension in AC, we've got the tension in AD, and we've got the balloon force. All right, so again, a lot of this is going to be rewriting. So we have the negative 0.6, 0.3243, 0. I'm going to do the balloon force actually later. We'll fill that in here in a second. Remember, though, we're multiplying by the magnitude. Okay, so for this, I'm going to call that TAC. I'm going to call this TAB. All right. And then that's I plus. Then we start doing our J component. So we have, what is that, negative 0.7568, negative 0.8615. But don't forget your constant, TAC, TAD, J, 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 plus okay, and so that one's 0. That's 0.5676, and that's TAC. Negative 0.5077 TAD. And then we've got our K. Okay, now the one thing that we haven't filled out is the balloon force. Now, let me scroll up a bit. I don't like scrolling up and down too much, but here's the problem. Can somebody just tell me what is the balloon force? Remember, the balloon had a magnitude of 800 newtons. So if I were to write that as a vector, what would be the balloon force vector? I'll stand like this because I have it written. 800J, and it's a positive 800J because it's going upwards. That's exactly right. So this is 0, and this is 800 newtons. That's 0. That's exactly right. So I have that negative there that I got to fix, which I'll probably have to redo in some of my solution, but I think so far everything else I've got is correct. I'm actually going to stop my share here for a second. I want to show y'all what I got going on the board. So if you look here on the board, you can see I've got this written in the same format I had here. And I find this to be very, very easy when you're doing your 3D equilibrium, because if you're neat about how you line everything up, then what do you have here? You've got 4 forces, and these are the I components, these are the components, these are the K components. All I have to do is sum forces in the X direction, some forces in the Y direction, some forces in the Z direction, and if you're halfway neat about it, it makes that summation of forces so much easier, okay? So, again, I just kind of wanted to point that out. Okay, so now what we can do is we can apply equilibrium. All right, let me look at this. Ooh, man, that scroll gets ahead of me. So now our static equilibrium. Okay, So now what we're going to do is we're going to sum forces in the x direction. And all you have to do is go off of your columns, okay? So when I sum forces in the x direction, I'm going to sum all of the forces that are associated with an I vector. And so what is that? It's negative 0.6 TAB plus 0.3243 TAC. And then this might seem a little silly, but you'll see why I'm doing it. Plus 0 TAD is 0. The reason I'm writing it like that is because there are 3 unknowns, the TAB, the TAC, and the TAD, and so at least I have it written out. Okay, there's a 0 on that term, and you'll see why here in a second. Now let's sum forces in the y direction. So I have negative 0.8 TAB minus 0.7568 TAC minus 0.8615 TAD plus 800 newtons equals 0. Okay, and you can do, now this is actually an interesting point. You can do this however you want. You could say, I'm going to move the 800 newtons over to the right side of the equation, and then everything would be negative. Or you can move everything else onto the left, everything else onto the right side of the equation and keep everything positive. In other words, like if I subtract 800 newtons from either side, then every term is going to be negative. I'm late. I don't like dealing with all those negatives. I'm a positive person, so I'm going to just keep everything positive and say 0.8 TAB plus 0.756868. What am I doing? 68 TAC plus 0.8615 TAD is 800 newtons. And so that's my second equation. And again, that's just an algebra part. Well, now you stealing my thunder, Mr. Davis. But you're probably right. All right. And so now let's do this one. Okay, so we have, you're fine. We'll go ahead and knock it out. So 0 TAB plus 0.5676 TAC minus 0.5077 TAD is 0. And so that is equation 3. All right. So yeah, like you'll see, like if you get comfortable with this, you just kind of, the process is pretty repetitive and pretty straightforward. All right. So now, oh goodness gracious, that scroll, I'm telling you, it has a mind of its own. Okay. So now I've got my 3 equations of equilibrium. Now what I'm going to do is written in matrix form. So write these equations in matrix form. All right. And so what I mean by that is I just take each equation one at a time and I say minus 0.6, 0.3243, 0, and then 0. And so the way you have them written out, you have a pile of junk times TAB plus a pile of junk times TAC plus a pile of junk times TAD equals, another pile of junk. it sort of makes your life easier, you know, in terms of writing it. This is 0.8, this is 0.7568, this is 0.8615, and that's 800 newtons. And then this is 0, this is 0.5676 minus 0.5077, and that's 0. And what are my unknowns? My unknowns are TAB, TAC, TAD. Okay, and so they're written in that order. So your calculator will spit out the TAB solution first, the TAC solution second, and the TAD solution third. So just make sure, again, it's all proper bookkeeping. And so now it's, you know, breaking out the Casio and chugging this out. So I'm going to do this with you, actually. So because I think I had, or did I not have, let's see. No, I think I was good on this part. I just had a typo up here on the board. So let's go to System Solver 3 by 3. This is 0.3243. This is 0. This is 0.8. This is 7567. Let's see. This is 0.8615. How do you decide which row is assigned to which tension? Give me 1 sec and I'm going to answer that because that's a really good question. This is 0, this is 567, this is negative. Okay, so when I did this in the calculator, like I did this in my TI-36X, it actually gave me fractions, 44. All right, so let me just make sure I did mine right. Yeah, and then yeah, okay. So I want to make sure, I want to see if anybody else is getting Mr. Davis's answer. So I'm going to wait in the chat on that. Although one thing I will mention, Mr. Davis, you mentioned you have a lot of negative answers, and all my answers came out positive. So you might want to check that. Now, how do you decide? Now, Mr. Brown asks, how do you decide which row is assigned to which tension? Really, what it is this. So let me go up to here. Okay. If you look at the way the equations are written, let me check the. Let's investigate this a little bit. I've got 2 different questions, so let's take them one at a time. The reason why I have which row assigned to which tension was just the way that I wrote it out. Like if you look here, see how I've got the force vectors written like this is times TAB, this is times TAC, this is times TAD, this is times 0. So when I write the equation out, I just did TAB first. I could have very easily swapped the rows. I could have easily done, you know, TAC first and then done TAD and then done TAB. It really wouldn't matter. The only thing that it would do is it would change maybe the order and how this matrix is written out. You would get the same numbers. You would just get the same numbers. You would just get them in a different order. So it's not really it's not really a matter of like how did I decide. It's just the cables were called AB, AC, and AD, so I just wrote them in that order, and I just tracked which one was written. I just did it alphabetically. Now remember, it might have been a while since you did this from did matrix multiplication, but when if you look at this the way this is written, you're going to take this times this plus this times that plus that times that equals that. Okay, that is like that first equation. Like so, negative 0.6 times this, 0.3243 times this, 0 times that. Hopefully I answered that that question. But if not, like if you need some clarification, let me know. Now, for the folks that are getting negative, let me ask you a question. Here, let me pull up the board here for a second. For the folks that are getting negative answers. Okay, so let me ask you this. Is this what it looks like, but that's negative? Is that what you're doing? For the folks that are getting negative answers. Like, is this one negative? Well, we had negative. Yeah, okay, yeah. See, I see. Let me say this. Let me, if you're watching the screen, watch this. Okay. You should get the same answer if this is negative, but they're all negative. Like if they're all negative, you should get the same answer. That's why, yeah. So if they're all negative, but that's positive, that'll do it. That'll flip all your answers. Yeah, that'll do it. All right. Is there any way you could show your calculator screen? I'm not exactly sure what we're putting in. Let me see, actually. Now I have a TI-36, so it's a bit different, but I can give it a shot. I don't have one with me, but let me see something. Actually, let me try something out. I actually have an app on my phone that is a Casio calculator. Oh goodness, the app has ads though. Let me see. System. Okay, so this is going to be kind of weird, but let's see if this works. Oh, this is weird. Bear with me. Okay. So you should see something on your screen that kind of looks something like this. It might look a little different. And so first thing you should do is when you press mode, so it should be mode, then 5, and then 2. So when you press the mode button and you do option 5 and then option 2, it should look like this. And then what you're doing is you're just entering in those values. So that first term would be 0.6, then this term would be 0.3243, and then 0. Oh, I wasn't done. And then this term is minus 0.8. I'm going to do the minuses. Minus 0.7568. Like this should be kind of what it looks like. Were you able to get that figured out? Here, I'll see if I can chug it out. Wait, what? I get that what happens in the fourth row? There shouldn't be a fourth row. It should be like a table that's 3 by, like it should be 3 by 4. So like what you should have is the 4. Okay, so the okay. All right. The fourth column. Oh, hold on. The fourth column are these numbers here. So since I've got all these negative, that one will be negative, right? So so this is your 3 by 3, and then the fourth column is this number. See, whenever you have a linear system, like a system of equations, it's defined by these constants and then these numbers. Yeah. So you should. So when you enter this in your calculator, it should be like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then it should give you a value here for x, a value here for y, and a value here for z. Because the calculator doesn't know what we're calling these things. Like we're calling them TAB, TAC, and TAD. The calculator doesn't understand that, so it's just going to say that this is x, this is y, and this is z. So let me go back to the screen share. Okay, so in the Casio, so you go mode 5, 2, and then so this should be the table of numbers that you enter in, and then it should spit out the following answers. So it should say something like x equals 200.91, y equals 371.69, and z equals 415.53. Okay, and so what that means then is cable AB is experiencing a tensile force of 200.91 newtons. TAC is experiencing, or cable AC is experiencing a tensile force of 371.69 newtons, and then TAD, cable AD is experiencing a tensile force of 415.53 newtons. Okay. All right. I want to take a sec and make sure that everybody's comfortable with this, because not only is this something that you're going to need to do on homework assignments, but solving these systems more than likely is something that you'll need to do on your exam. So if you're comfortable with this, then you're good. If not, let's hash that out. Any questions? All right. So a couple things. You all will have a homework assignment due Friday. I'll probably end up seeing a couple of you in class later, right? Because I'll be covering lab for geomatics. So some of you will probably be in there. Now I'll tell you, I had a geomatics lab yesterday, and I told them that I said that I would, I should have come prepared, with like some jokes, but I didn't think of them in advance. I didn't have the foresight to think of those jokes in advance. Because get foresight. Yeah, I haven't thrown too many jokes in there. I haven't thrown too many jokes in this class. It feels like sometimes I got to force them in. It's bad. It's really tough to tell jokes. When you're by yourself. So I'm telling you, they're bad. They're really bad jokes. All right, everybody. All right, so okay, thank you, thank you. So we got some folks that appreciate some BAPA. I'm a dad, so I have the dad jokes, and I can say that. Okay, all right. We're gonna go ahead and call it. We're gonna go ahead and call it a few minutes early because that's good. And this is it for the exam. We're gonna have a lecture on Friday, but this, if you can do this and do the homework assignment due Friday, that's everything up until the exam. Way to force those jokes. Of course, yeah, yeah. That's what I got to do. All right, I'm going to call it. Everybody, stay safe, stay healthy. For those of you in geomatics, I'll see you in about an hour and a half. So that's all I got.